In section 11.5, we're going to learn how to find the area of regular polygons, and this is a little bit challenging and it involves several key things that we've learned from earlier on in the year, okay? Couple of quick reviews. Number one, you need to know angle measures, okay? So this is a regular hexagon. I would like to find the area of this regular hexagon. And I want angle measures, okay? I hope you remember the angle measures of hexagons, okay? It's a pretty basic fact. You really need to know what the angle measures of regular pentagons, regular hexagons, regular octagons, at least know those three, okay? However, if you forgot, remember that you can find the interior angle sum by multiplying the number of sides minus 2 times 180 degrees, okay? So for a hexagon, 6 minus 2 would be 4, okay? 4 times 180 would be 720 degrees, okay? There's 6 angles. If I divide 720 by 6, I find out that each of these angle measures is 120 degrees, okay? Great way to do this, okay? The second idea that you might want to try using, and it might be a lot easier for a lot of you, especially to do it in your head, remember that the exterior angle sum is always 360 degrees, okay? So for example, if I extend the exterior angles off in this direction all the way around, there would be 6 exterior angles if I extend out to the right-hand side, okay? 360 divided by 6 is gonna give me 60 degrees, okay? So if the exterior angle is 60, these have to be supplementary. So subtract 60 from 180, you get 120, okay? One way or another, you need to know how to find angles of regular polygons. But I would memorize, pentagons have 108 degree angles, hexagons have 120 degree angles, octagons have 135 degree angles. It'll save you some time, okay? But make sure you know those formulas. You'll need that for the ACT as well. Okay, let's come back to this hexagon. There are lots of different ways you can break these things up, okay? However, the way we're gonna break these up, we're gonna try to get a consistent approach that'll work for every kind of shape, regardless of the number of sides. So I'm gonna pick a point in the center, and I'm gonna create kind of a spokes pattern to create triangles like this, okay? And remember that these are 120 degree angles, so they're getting bisected if this is regular. If it's regular, it's got equal side lengths, equal angle measures. That's gonna be 60, that's gonna be 60, that's gonna force that to be 60, okay? A really key fact, hexagons break up into 6 equilateral triangles, okay? So really all we've gotta do is find the area of one of those equilateral triangles, and there are just 6 of those congruent triangles, and we've got the area of the whole thing, okay? So you've got a couple different options. You can remember that the area of a triangle is half the base times the height. Some of you might remember that the area of an equilateral triangle is the side squared divided by 4 times radical 3, okay? Either one of those you can use, doesn't matter which one. So just using the basic approach, remember you can divide an equilateral triangle into little 30, 60, 90 triangles. So this length here is gonna be 3, this side here is gonna be 3 radical 3, okay? So half the base length was 6, times the height of 3 radical 3, and I think we end up getting 9 radical 3 for the area of one of those triangles, okay? You're gonna have 6 9 radical 3s going all the way around to create that hexagon. Or by the way, could have done it much faster. The side squared, 6 squared is 36, divided by 4 is 9, and then you're multiplying by radical 3, and you get 9 radical 3. So either one of those approaches should work, all right? We have 6 triangles with areas of 9 radical 3, all right? 6 times 9 is 54. 54 radical 3 square units would be the area of that hexagon, okay? Really nice, works out very well, not a big deal, okay? Just to try one more here. The numbers are a little bit nicer if you have whole number values. So I don't know why I erased that whole shape, but let's do this again. Let's say the side lengths are 10. I know I'm making this look smaller, but let's say the sides are 10. Same kind of thing. We can break it up in that kind of spokes pattern toward the center. And again, those are 120 degree angles, so they're breaking up into 60, 60, 60, 60, all the way around. The other thing is, you've got 6 angles that make a complete circle here. So those 6 angles need to add up to 360 degrees. That's another reason you can see that you have 60 degree angles, okay? So the area of one of those triangles, you'd have a side length of 10. This side would be 5. It's a little 30, 60, 90 triangle. Height's going to be 5 radical 3, okay? So the area of one triangle can be half the base of 10 times the height of 5 radical 3. Half of 50 radical 3 is going to be 25 radical 3, okay? Or you could do the sides squared. 10 squared is 100, divided by 4 is 25 radical 3. You have 6 triangles with areas of 25 radical 3. So 6 times 25, I believe is 150. 150 radical 3 square units would be the area of that hexagon, okay? So pretty predictable, hopefully not something that's terribly difficult.